we can actually bring in some of these calculations into a delta H value, writing thermochemical equations. So I think about this thermochemical equation is just more or less the same thing as a balanced chemical equation with the delta H information included. So think about that, and we'll write out one for methane. So on your paper, we're writing CH4, that's our methane molecule, plus 2 moles of oxygen. These are all in the gaseous phase, forming a mole of carbon dioxide gas and 2 moles of water. And as part of that, you're going to write delta H is negative 213 kcals per mole. You're just including the delta H value right at the end of your chemical sentence. Now I want you to notice the negative sign. Negative sign means heat releasing. It's exothermic. Exothermic reactions release energy from the system to the surroundings. Exothermic. Well, this is actually an endothermic graph. The exothermic graph, if I may, just compare the two quickly. Let's do a compare and contrast. In an exothermic, we have the reactants of higher energy than the products, and that's what this reaction would show, exothermic. We would have the reactants and the products separated by an energy hill. We'll learn to label that as the activation energy. When we see a diagram that shows the reactants of higher energy than the products, this is our value here of delta H, the heat of reaction. And notice that if delta H is negative, that's an exothermic process. And that means the reactants released energy. And we would just say in this example, as I read that amount, 213, on our graph, that would be 213 kcals difference between the products and the reactants. The reactants let off 213 kcals of energy. And the reason I redrew that is, notice here, I have a graph where I have reactants climbing this energy barrier called the activation energy, and the products actually ended at a higher state. Well, this is an endothermic process, meaning that energy is absorbed and it's required. So the activation energy, again, from the point where you see the reactants up to the very top of the hill, that's called the activation energy. How much energy is needed to start the equation? Since the products are of higher energy than the reactants, the delta H here, the heat of the reaction, comes out positive. So we'll compare those graphs in an exo and endothermic process. Drawing the energy diagram for methane is this requirement. Methane released 213 kcals of energy. Now if we consider this reaction where carbon dioxide and water form glucose and oxygen, this is the thermochemical equation for photosynthesis. 6 moles of carbon dioxide in the gaseous form, plus 6 moles of water in a liquid form, react to form 1 molecule of glucose, C6H12O6, and 6 molecules of oxygen. The thermochemical equation includes the delta H at the end of your chemical sentence. So thermochemical equation says, write out your balanced chemical equation, and at the end of your sentence, include the information about delta H. Now notice this is a positive sign, meaning that it's heat absorbing. And if I'm absorbing energy, it's an endothermic process. And this is the graph that we'll draw for an endothermic process. And this is actually correct. The reactants climb an energy barrier and end at a higher amount of energy than the initial reactants. So reactants go to products. I'll just write R and P. You can do the same. With its energy diagram, we're learning the activation energy is the amount of energy needed to go across this little energy barrier. I'm going to abbreviate that as EA, the activation energy. And down here, the difference between the reactants and the products is your heat of reaction. And since we're at a higher value, positive 678 kcals should be labeled on your graph. So as reactants climbed to products, it had to absorb 678 kcals per mole. So we're just looking at energy changes, heat releasing, heat absorbing, kind of sprinkling in actually the next section as well, talking about energy diagrams. If you see the reactants of lower energy as compared to the products, it is endothermic. If you see, as in what we drew here, the reactants of higher energy as compared to the products, that's how we know it was exothermic. Our energy diagrams compare the amount of energy stored in the bonds of the reactants as compared to the products. Let's consider this. When two molecules of ammonia, NH3, decompose, this is a decomposition problem, it decomposes to form 3 molecules of hydrogen and 1 molecule of nitrogen. To do so, the delta H is included as 22 kcals per mole, and notice its sign is positive. This is a thermochemical equation. It's a balanced chemical equation that includes the delta H information. I want you to think, and the true definition of this is enthalpy, which is a thermodynamic property related to heat. But it's really okay to just think of delta H as the heat. How much heat is being absorbed or released during this reaction? Well, from a thermochemical equation, to know if it's being absorbed or released, we simply look at the sign. The sign on delta H we see is positive. So a positive delta H indicates that it is an endothermic reaction, meaning heat is being absorbed. It is required for the reaction to occur. Requiring energy means that the reactants are stronger bonds than the products. So all endothermic reactions, the reactants have stronger bonds than the products. And the opposite would be true, right? If it were exothermic, the products would have stronger bonds, heat releasing. So if you think about this energy diagram, I would have the reactants down low and the products up high. The reactants turn to products. And just think about, here's our energy on the y-axis, and just saying as energy goes up, the difference between the reactants and products is known as your delta H. And this would need to absorb 22 kcals of energy for every mole of reactant. So there's your visual of an endothermic reaction, absorbing energy. So clearly you see the reactants are of lower energy. The reactants are. In that graph, just to emphasize, reactants absorb to go to products. The reactants are here of lower energy. The products are up here, so therefore they're of higher energy. And this is an endothermic process. Heat is being absorbed. digest that, huh? How about trying this one on your own? Well, this is going to involve a little calculation. So, well, let's try this together. I'm not going to ask you to try it on your own unless you want to pause and just kind of process, take a little break, but I'll go ahead and kind of model the first one. We're looking at a thermochemical equation. And I know that the thermochemical equation is just a balanced chemical equation that includes the heat of reaction. And that is going to allow us to see that this is an exothermic process. And just to think about that, we have an exothermic, meaning the reactants go to products where the heat is being released. So as reactants turn to products, our delta H, the difference between the energy level of reactants to products, is negative 531 kJs. We'll also learn to define this area as the activation energy, E sub A, how much energy is needed to separate the reactants and products. But the delta H is the difference between the reactants and products. And we'll practice that in our section 3. I'm just seeding that so it's easier when we get there. The combustion of propane, C3H8, with oxygen occurs with the balanced chemical equation, and it releases 531 kcals of energy. How many kilocalories of energy are released when 0.75 moles of propane are burned? Well, this is a conversion. So this is our given amount. We have 0.750 moles of propane. And this is just a conversion of, we've been practicing, what do we want from given? Well, we want to solve for kilocalories given the number of moles of propane. Given a mole, calculate a kilocalorie of energy. From your balanced equation, we have negative 531 kcals. See how that's just right here as part of your balanced equation? And the number in front of the propane here is 1. So this is what we would call our stoichiometric ratio. The little heart of our problem in the stoichiometric ratio, our want over given. We want to know kcals. From the balanced equation, it's negative 531. We were given moles of propane. From the balanced equation, its coefficient is 1. So let's go ahead and solve that. 0.75 times negative 531. And my screen reads, well, I'll write it down here, negative 398.25. Let's turn that into 3 sig figs. So negative 398 kcals of energy released. A one-step mole conversion, really, where we're inviting kcals into the stoichiometric ratio. Shall we try one more together? What if we're given 1 mole of molecular oxygen and we're asked to solve for kcals of energy? With this conversion, we want to know kcals given moles of oxygen. And just think about your want over given ratio from the balanced thermochemical equation. Those conversion factors just come from your equation, don't they? We want to know kcals. Its coefficient, or its value here, is negative 531 from the balanced equation. And we started with moles of oxygen. Its coefficient from the balanced equation is a 5. So our ratio, our want over given ratio, negative 531 kcals for every 5 moles of oxygen. And when you solve for that, 1 times 531 divided by 5. And my screen reads negative 106.2, but we should probably just carry the 3 sig figs. Negative 106 kcals of energy. We just practiced doing mole conversions using balanced chemical equations. Now that I've modeled 2 of those problems, I'll encourage you to try the others on your own and come back to the video when you're ready to check. You have a few problems on the remainder of page 6. Welcome back. Let's check out our work. Using the given delta H and the balanced equation for the reaction of magnesium with water, how many kcals of energy are released when 4 grams of magnesium are used? We're given 4.00 grams of Mg. Now I know that coefficients stand for moles. So therefore, no matter what unit I'm given, my job is to get it to a mole. So in step 1 of our stoichiometry roadmap, we divide, whoops, let me write that correctly. You divide to head into the mole, and we're going to divide by molar mass to convert into a mole. So in my first conversion, I had to go and find the molar mass of a magnesium atom, and I report that as 24.3 grams. So just to remind myself, we divide to head into the mole, and our conversion factor is called molar mass. Then on our stoichiometry roadmap, we ratio. Our ratio is always want over given. We want to know kcals. This is an exothermic reaction. I see the negative sign, negative 83.9 kcals of energy. And I started at magnesium, whose coefficient is a 1. In our first step, we divided to convert to a mole. In the second step, we ratioed. And our last step here will just be to calculate to end at kcals. So we have 4 divided by 24.3 times negative 83.9. My screen reads negative 13.81. I'm going to use my 3 sig fig rule, so negative 13.8 kilocalories of energy. How'd you do? Shall we continue? You have 3 more to practice with the glucose. Let's write this equation. We have C6H12O6, and it made 2 molecules of ethanol and 2 molecules of carbon dioxide, and in doing so it released 16 kcals of energy. So this is our thermochemical equation. That's a balanced chemical equation that includes the delta H information, the heat of reaction. In letter A, we'd like to know kilocalories, starting with 6 moles of glucose. So your given quantity already in the mole, very nice. So really all we need on the stoichiometry roadmap is the second step, the ratio, our want over given stoichiometric ratio. So from the balanced equation, negative 16 kcals, starting with 1 mole of glucose. So your ratio here, your want over given ratio, kcals per mole. The coefficient of glucose happens to be a 1. So here I'll hit 16, it's not 16, 6 times negative 16, and I find negative 96 kcals. Does that match your paper? I bet it does. You're doing great work. How about letter B? You started with 1 mole of ethanol. That was your C2H6O, and we want to know kcals. We see that negative 16 kcals from our balanced equation. And now notice that we have a coefficient of 2 in front of the ethanol. So that means for 2 moles of C2H6O. So the ratio of want over given is negative 16 over 2. And when I solve for that, negative 8 kcals are released. How about letter C? I'm going to give myself more room. This is 20 grams of glucose. And we want to know kilocalories. So that means we have to get into the mole first. So step 1, we divide by molar mass. Then we can ratio. So I've got to go to work and find the molar mass of C6H12O6. I know carbon has a molar mass of 12, and I see 6 of them in the formula. Hydrogen has a molar mass of 1, and there's 12 of them in the formula. And oxygen has a molar mass of 16, and there's 6 of them in the formula. So I'm going to count 12 times 6 plus 12 plus 16 times 6, and you find a molar mass of this sugar molecule as 180 grams. Now we can set up our want over given ratio. From our balanced equation, oops, I scrolled too far down, it was negative 16 kcals. And what about that coefficient in front of the glucose? Oh, right here, it's a 1. So there's our ratio step. Step 1, divide. Step 2, your ratio, and that will land us at the kcals of energy. And we know it will be an exothermic answer. 20 divided by the molar mass of 180 times negative 16. And this gives me negative 1.78. Now I'm going back and saying this is good, 2 sig figs. And letter B should actually have 2 sig figs, so I'll do 8.0. And in letter C, we should actually have 3 sig figs, so I'm good there. Just considering that. 8.0 kcals for letter B would be the accurate sig fig answer. We did it. We've checked our work. We've accomplished through page 6. In your next video lesson, we'll come back and talk about energy diagrams. But I'll be honest, because I'm sneaky, we've already talked a lot about energy diagrams by drawing endo and exothermic reactions. Take a break, come back to your next lesson when ready.